Yeah. So whole part of this complete a deep learning concept to update the weight and bias. That's all. And that's what whatever things is getting changeable, that part is called as learnable parameter, right? That things in deep learning is concept is called as learnable parameter. So what are the learnable parameters here? So W, weights are and bias are learnable parameter because these things value is getting changed. With the time, it is getting changed. Did you understood? So here is our actual, this is going to our neuron and this is coming under the function. So this is input and this input is going to pass to the activation function. So we are going to talk about this activation function in today's session. This is nothing but it's called as activation function. Activation function. So we are going to discuss about this part only. You can see here we are going to pass the input. So here it is coming like input, right? In this neuron, if I'm going to consider what are the inputs is coming to this neuron. What are the inputs is coming to this neuron? This neuron. I'm talking about this neuron. Just think about this neuron. So see, W1 is coming and W3 is coming, W5 is coming, and W7 is coming, right? So if I'm not wrong, W1 X1, W3 X3, W5 X5, wait a minute, W1 X1, W3 X2, W5 X3, and W7 X4, right? This things is coming plus one additional term because see here one thing is coming additionally which is called bias. I will talk about this why this bias it is. So this is going to this neuron. This is the input for this neuron, and whatever input we passed to this neuron, this input we are going to pass through one another function which is called activation function. So we are going to discuss about this activation function, and the output of this activation function will pass to the another output layer. This is which is called output layer, and this output of this activation function will pass to the as a input to the output layer. Did you understand? Concepts are clear? Yeah. Similarly, for this neuron, what will be the input? So simple, X1 W2 plus X, all the even numbers of weights, right? So X2 W4 plus X3 W6 plus X4 W8, right? And plus B. B means bias. Again, here is also B. Again, you must ask what is W1, W2, W4, and these things. You just understand W1, W2, W3 is everything. W and B is the randomly initialized weight. I will talk about what is initialization techniques, but as of now, just try to understand this is the randomly initialized thing, like 0.1, 0.2, whatever things you can understand. And again, you are going to pass through the one activation function, and the output of this activation function will go to the another layer. If there is a further hidden layer, then it will go to the further hidden layer. If no, then it will directly jump into the output layer. So now, if I will talk about what is the input for this output layer. So input for this output layer, very simple. So input of the output layer, output of this function and output of this function, right? So input of the output layer. So output layer ka input equal to F1 and W1 X3 plus W2 W3 X1, this is X1. W1 X1. W3 X2. W5 X3 plus W7 X4 plus B plus F2 so here it will come like W2 X1 W4 X2 plus W6 X3 plus W8 X4 plus B. This will be the, again, in this output layer, again, there is a one bias. There should be one bias. So you can consider, again, the capital, additional capital. Bias will be always there. So this will be the input. Again, this is not an output of output layer. This is the input of the output function. This is going as an input. Now, output of output layer will be what? Again, there will be one activation function. And the output, this one. Okay. Did you understand what I'm trying to say? And again, output layer may what are the each hidden layer may consider different type of activation function. We'll talk about that. It can be sigmoid, it can be ReLU, it can be leaky ReLU. All these things we will talk about this in detailed discussion. Right now, any questions so far? So far, are we good so far? What is hidden layer? What is activation function? Activation function is utilized for to activate the neuron, and it will take a decision whether the neuron has to activate it or not. Simple. Let's suppose if something is going to come inside of your eye, then the pain will come in your eye, not on your hand or leg, right? So that moment, hand and leg neuron will be deactivated, but eye neuron will get activated to send the signal continuously to the brain what to take the action. Did you understand what I'm trying to say? Yeah. Yes. So in that way, it is going to be considered like this. Okay, very nice. So why it is coming here? I cannot clear this. Oh, that's fine. Okay. So let's consider then what are different type of activation function it is. Okay, parallelly I'm opening again. Okay, this theory part, what is activation function? Everything has been written in your slide. I have already uploaded, so you can walk through that thing. So commonly used activation function. So what are the different type of activation functions are there? Let's talk about that. So commonly used activation function. Number one, very popular, called sigmoid activation function. And don't worry, these are the notes is already given. Okay, so everything is written there. Sigmoid activation function. One minute. Yes. Hello. Yeah. So you got the presentation, right? Slides and all those sort of things. Okay. Okay. If you have not received, can you please send a mail regarding for that? Like you have not received your slides and all. And please do mention your mail ID, registered mail ID. Okay. Yeah. Because we already shared. But if in case if you have not received, then please share me, DM me that your mail ID. I'll see. Yeah. So, cool. No, please. Thank you. Okay, the sigmoid activation function. So the function formula, what is the sigmoid activation function formula is very simple. Sigma of x equal to 1 by 1 plus e to the power minus x. This is our sigmoid activation function. And method and representation wise, if you're going to consider sigmoid activation function representation, then it is something look like this. So this is our sigmoid. So sigmoid activation function, function input, you can see this is like zero centric, right? The center value of this function is falling. No, sorry, it's not zero centric, but it's correct. And the value lie between 0 and 1. Output of this function lie between 0 and 1. Just hello. चलो बढ़िया है, हैप्पी जर्नी. 14 को लिखिए। बढ़िया है। ठीक है, मिलते हैं कोलकाता में। चलो, खाना वाना हो गया? ठीक है, ठीक है। सिया, so so the sigmoid function is basically where we are going to use the sigmoid activation function. Generally, you can use sigmoid activation function wherever you want, but as a convention, as a whenever researchers develop the sigmoid activation function, they 1 minute actually. My wife is going to move down. Hello, class लेना, I'll call you back. हाँ, sure. Yeah, I'll call you. तुम नहीं लियो अपना? हाँ ठीक है, मैं आऊंगा 15 को। तुम सब घूम करके रखना, फिर लास्ट में मैं आता हूँ। ओके, मैं 6 बजे तक कॉल करूँगा। ठीक है, I'm taking the class. I'll call you. Sorry. So sigmoid function is the most frequently used activation function. Generally, sigmoid activation function, where we are going to use the sigmoid activation function, it's very common. So you just try to understand, replicate this diagram once again. This is our input layer, and this is our hidden layer. This is our output layer. And here just try to understand this way: x1, x2, x3. Let's just try to understand this part. Again, I'm drawing the same diagram. So, yeah. Okay, pretty much cool. Okay. So whenever we are talking about the hidden layer, in the hidden layer, we never apply the sigmoid activation function. Sigmoid activation function, I'm not talking about the never going to apply. It depends on the research. Whatever research I have done so far, so forth on the deep learning side, sigmoid activation function we are going to use at the output layer. Okay, so sigmoid activation function we are going to use at the output layer. Okay, so at the output layer, we are going to use always sigmoid activation function. Now, again, the concept is here. So when sigmoid activation function we have to use at the output layer, when your output is binary class, binary category, means either yes, no, true, false, male, female, yes, no, this kind of thing, then you should apply sigmoid activation function. Did you understand what I'm trying to say? Sigmoid activation function you should not apply anytime on this place, hidden layer. In this place, we are going to apply different activation function, but sigmoid activation function we are not going to apply it here. Did you understand what I'm trying to say?
So, and in output layer also, you are telling that whenever it is a binary output kind of thing, then only.
Correct. So when the binary class category, then you should apply the, because see in this diagram you can consider this is more about the if you could recall logistic regression, there also we apply the sigmoid function, right? Yeah. So ultimately it's a linear it's a live regression problem only, but whatever output is coming from the regression we are going to pass through the sigmoid function, and the sigmoid function is giving 0 and 1, either 0 and 1. So if the value is above 0.5, then we are going to consider as a 1. If the value is less than 0.5, then we are going to consider as a 0 value, right? So that's a thing, that's why we are going to apply these things there. Okay, so now there is just some defects in the sigmoid activation function. So what are those defects? So number one defects, the function output, some text box, text box. The function output is not centered to 0, or we can say 0 centered, which will reduce the efficiency in weight update. Okay, this is the number one defect. And number two defect is the sigmoid function perform exponential operation which is slower for computers. So you can see, if you can consider this function, you can see this like at the exponential function, right? E power part. So which is slower for computers. Okay, very good. So these are the major disadvantage of the sigmoid activation function. Okay. Now coming to the part of some advantages also is there in sigmoid activation function. What are those? So if I'll consider advantage of sigmoid activation function, number one, smooth gradient. What I'm trying to say, smooth gradient in the sense of, and basically, I was talking about this parabola, right? In this parabola, what we have discussed, our main agenda is to reach this global minimum. And sigmoid activation function is very smooth. If you can see this graph, this is very smooth, right? So with this, what will happen? It will not prone towards exploding gradient descent problem. What do you mean by the exploding gradient descent problem? Means it is
somewhere it will be stopped.
Correct. Means it's not like that. First time after updating the weights and bias, the neurons are here. Then second time it will come here, third time it will come here, and fourth time it will come here, and fifth time it came out. So it will never reach to this. This kind of problem will never getting occur because of this smoothness. Because of this smoothness, neurons is moving towards the global minima very slowly, very slowly, and it reached to the global minima. So exploding gradient descent problem will not occur due to this smooth gradient. So smooth gradient prevent exploding gradient descent problem. Gradient descent problem. Okay, nice. So number two, output value bound between 0 and 1. So what do you mean by that? Just now I explained. If output value is lying between 0 and 1, then normalization don't need, right? So you were speaking about earlier only, right? Okay, I got that. Where we have to apply the standardization. I told you, right? If the input feature is continuous type of data, not categorical. So if the categorical means 0 or 1, right? Or 1, 2, 3, this kind of thing, then we can't apply the normalization there. We should not apply the normalization. So if the output value lie between 0 and 1, so the values are already normalized. So normalizing the output is not required, right? So normalizing the output not required. It's already normalized. Okay. Third. So third is clear prediction. Clear prediction that is very close to 1 or 0. That is very close to 1 or 0. Okay. So that is called advantage. Now we get to know disadvantage and advantage, all the sort of things, right? So now okay, this is about the sigmoid activation function. So overall, what we understood about the sigmoid activation function? Sigmoid activation function is exponential function, means it's number one, like this sigmoid activation function we should apply at the output layer, number 1 point. And only in what condition? When the output is categorical type of or binary classification. Then you should apply the sigmoid activation function. And disadvantage is what? It's not zero-centered, right? Number two, as it is an exponential function, so computer takes time to compute, and as it is slower, then exploding gradient descent problem will not occur. This is called advantage. And the clear prediction, because very close to 1 or 0, either value will be 1 or 0. This is called our first activation function. Any question?
No.
No question. Good. So now let's talk about another activation function called tanh. Now, tanh. It's called tan hyperbolic function. Tanh activation function. So let me draw this image first. Okay. So this is called as tan activation function. So, so tan activation function can be defined like this. Tan x is equal to e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. This is called tan hyperbolic function. Tan is a hyperbolic tangent function. And the curve of the tan h function and sigmoid function are relatively similar. You can see, right? If you can consider the sigmoid and tan h, it's quite similar, right? But only difference is that you can see the output is zero-centric, right? Similar, right?
Yeah.
There is only difference. The output of the tan h is the zero-centric. So what I'm trying to say, when the input is large or small, the output is almost smooth and gradient is small, and which is not conductive weight and update. So what I'm trying to say in this case, so this is our tan h function, right? And this tan h function advantage is what? What are the advantages are there? Do you guys celebrate Diwali?
No.
No?
Yeah.
Acha, acha. South India, which festival do you guys celebrate very in a bigger way?
Dasara.
Dasara. Ganesh Puja also people used to celebrate.
Yeah.
But in our case, like we used to celebrate our Chhat Puja. I don't know if you know or not, but at the north side, like Bihar or Jharkhand or Bengal side, the bill is very popular about the Chhat Puja. It's a 3 days completely without.
On Diwali.
After Diwali 6 day, this festival used to come. So it's a very popular, very much. It's a bigger festival. Like people used to say, it's a Mahaparv kind of thing. So in our case, Diwali is also very popular. So advantage is what? The output of 10H is zero centric. Zero centric.
Why it is advantage?
Sorry? Is zero centric.
Why it is an advantage?
So 10H is the zero centric, right? So zero centric means the output lie is very balanced. But in this case, you can see it is not zero centric. So you might be confused what will be the threshold to calculate it is 1 or 0. Right. So that's a criteria to find it out what the optimal threshold I have to consider to get the probabilistic output. Whether the threshold I should consider 0.4, 0.8, what I have to consider. Right. So that's a very general problem if it is not zero centric. Right. And again, the value lie of the 10H, what is the value? Where? Minus 1 to plus 1. So the value lie between minus 1 to plus 1. And this 10H function, you can apply in any layer. Like you can apply either in the hidden layer as well as 10. You can apply at the output layer as well. It depends. Right? Okay. So this is called 10H function. Now, again, at the end, everyone is going to apply ReLU, sigmoid, this kind of thing only, or softmax. Okay, this is the very popular activation function. Sorry.
You didn't tell at which type of data we need like these.
10H you can apply all the cases, either it's categorical or continuous. Okay, so 10H we can apply in both the cases.
So normalization
normalization you no need to do because the value lie between 0 and minus 1 to plus 1, right? So again, it's a zero centric and the value is not above the 1, right? So if not above the 1, then why we have to apply the normalization? Generally, what do you mean by the normalization? Let's talk about this visual representation. Let's suppose if I'm going to say I need 600 square feet, one master bedroom, 600 square feet, one master bedroom, and 300 or 400 square feet, one guest room. This is my master bedroom. This is called guest room. And you can consider balcony and all those things is around 300 square feet. Okay, this is our total requirement. Now, just let's suppose if I want to plot this master bedroom, this guest room, and this complete home in pen or paper, can I able to plot 600 square feet here? No, right? So what to do if I can't play? If I can't draw, then I will take a imaginary part of the 600 square feet, which can fit in this diagram and which I can show this is the 600 square feet, right? So here what we are trying to do, according to this page dimension, I'm going to normalize this height and width. And I'm going to adjust here so that you can.
That is standardized.
Standardization and normalization, both the terms is same. There is no difference between standardization and normalization. It's a technical term only. Just simple way. What we called it as I forgot that name. Huh. I forgot that name, but I generally used to say this thing in Python when I was teaching. Function and method. Yes. So some people used to call it function and some people call it as a function method. So what is the difference between the function and method? There is no difference between a function and method. It's just a term like people used to make a confusion. Similarly, normalization and standardization, both are same. So if your value is between 1 and -1, then what you will do in the normalization? It's a very smaller number, right? You don't need to do any kind of normalization. If the value is above 1, 300, 400, that value you can't put on a piece of paper, right? You have to do that. Okay. So now coming to the third activation function, which is called ReLU activation function. Okay. So ReLU activation function is equal to max 0, x. So what do you mean by this? This value lie between if your input is above 0, then the output will be input is above 0 means x is greater than 0, greater than equal to 0, then output will be what? Output will be x.
One.
No. Just let me draw this diagram, then I can explain. Okay. Just first draw the diagram so that you can understand what I am trying to say here. Just see. If your input is above x 0 se bada, then output is equal to x. Whatever x is there, y is there. X is there, y is there. Means x is directly proportional to y or y is directly proportional to x. But if your input is less than 0, but if your input is less than 0, then y will always equal to 0. Can you see this?
0.
Can you see this? Yeah. So with this diagram, we can understand. So ReLU function is very popular activation function, which generally used in where? Used in hidden layer. Always. So it always apply on the hidden layer side. So ReLU activation function is actually a function that takes the maximum value. If your input is greater than equal to 0, then output will be proportional to the x. Okay. But if your input is less than 0, then output will be what? Output will be always 0. So here is some disadvantage in case of what? In case of ReLU activation function. What is the disadvantage in ReLU activation function? Just observe this function and bear with me. Let me take this diagram here once again. Select this.
That is like step function.
Sorry.
That is like step function.
I'm not able to understand what you're trying to say, but let me explain this and then I will come to this. So just observe this function in that way. Let's suppose your x input, this is called as input, right? This is our input. Let's suppose if your input is above 0 or greater than 0, then these neurons will not be deactivated. This neuron will be work functional as expected. But let's suppose this x1, x2 or anything is negative value. Then this neuron become a dead, right? Because the output of this always will be 0. Did you understand what I'm trying to say? Hello?
Yeah.
Yeah. So this is
output means y your time, right?
Correct.
Y will be the 0 if x value is negative. Yeah.
Yes. So if x will be negative, then the output of this neuron will be negative 0, and 0 means this neuron got dead neuron. Means in that case, ReLU functionality will not work. Right? So So just disadvantage I'm talking about. Number one, and very popular disadvantage. If input is negative, or you can say less than 0, then neurons will be considered as dead neuron. Okay. But there is some advantages as well. Advantage में क्या है? Like as you can see, there is no complex exponential term. It's a very simple y is equal to x function. So the calculation wise, it is very faster. So if you are going to apply this activation function on your neuron side, then the computation power will get enhanced. Okay, this is the means advantage of ReLU activation. But again, still we are using this activation function. If we know there is no negative value will come from the input side, then feel free we can use this activation function. We no need to consider all these things. So we understood the limitation of ReLU activation function. Now let's remove this drawback. How we can remove this drawback?
Why we have two graphs there?
Sorry.
We have two graphs here.
So ये like ReLU activation function. This is called differentiation of this function. What will be the differentiation of this? Can you see
what
this?
is the use of this?
So see, if you consider our
and that is what I'm telling, that is like a step function.
I'm not able to understand what do you mean by the step function. The chain rule, we have seen our last class, the chain rule, right? There we are going to apply the differentiation. So so in that case, we need the differentiation of this function. That's what I'm going to always put both the function graph. Right. Are you talking about the step function means that chain rule?
No, actually, this graph you are showing here. Usually we call
as a step function. Okay.
So I just wanted to know whether.
So step function is basically what I can see. This step function is generally like this, right? So this, right? This is called step function. But this is not a step function. This value is very static. The value will lie between 0 and 1. Yeah. So now we understood the drawback of ReLU function. So in order to avoid this ReLU activation drawback, there is another activation function came into the picture, which is called leaky ReLU activation function. Leaky ReLU activation function. Whenever you will go for interview, very popular question, what are the different activation functions you have used? You have to keep all these names. So leaky ReLU activation function, how it used, how it works, just try to understand. So this leaky ReLU activation function works like when x is greater than equal to 0, then it is simple, y is equal to x. Y ka value y is equal to x. But when x is less than 0, then y is equal to 0.01x. So it is not going to mark completely 0. It is just going to consider something so that the value will never become 0. Did you understand how they are going to overcome this kind of problem? And just tweaking the formula, and they are going to solve this, right? So this is called leaky ReLU activation function. And the graph of leaky ReLU activation function is something like this. Know that diagram?
In that case, it won't pass to origin.
Sorry.
In that case, it won't pass through origin.
It will pass through the origin. You can see this is going to pass through the origin, but the output is something above, not going to follow this x. Can you see this x? It is just below or above the x minus direction. In that way, it is going to work. Here also you can see there is a slightly difference between these things.
Yeah.
So that the neuron, dead neuron wala concept was coming, right? The problem was coming. So that problem will not occur in case of leaky dead. Okay? हाँ. ठीक है, good. Any question in this?
So, just doubting that. If it is passing to 0, then our y won't be 0.01, it will be 0.
Acha. So why you are going to consider, then in that case this will be considered, right? If the value of x will be 0, then in that case the above condition will get matched. And in that case x is 0, then y is equal to 0. That's fine. Input is 0, then what the need of output? That's okay, no? If you're not going to pass the any input, then why you are expecting output? Yeah. So it will not fall under this condition. X is 0, then second condition will not match. It will follow the first condition. Right? Okay. So in this leaky value, there is again one disadvantage is there. Okay, I need it 10 something. Wait a minute. Okay. Cool. So I was talking about there is just again still there is some disadvantages are there. What is that disadvantage in case of leaky value? You can see in case of x less than 0, the value of y is going to follow a very static rule. Like it is not learning anything, right? We are just multiplying something 0.01 and so that neuron will never get dead, but the value of neuron, that particular neuron will be very less, right? Because 0.01 is what? Even your input is something 100. And if you are going to multiply this input 100 to 0.01, say, the value will be what? 1, right? Output will be 1, right? So this is not an optimal solution. It just reduces the problem like dead neuron wala problem, but it is not going to give the proper solution. Did you understand? So in order to overcome this problem, there is another activation function came into the picture, which is called ELU, exponential linear unit. So what do you mean by exponential linear unit? Function. Okay. So just try to observe what I'm trying to say here. Let me first draw this diagram and then I could explain in a better way. So in this case, x is greater than 0, then y is follow the same rule, y is equal to x. But x is less than 0, then y, greater than equal to 0 and less than 0. Then y will follow some rule, which is equal to alpha into e to the power x minus 1. Okay, this is the logic. So what is alpha here? Again, alpha is learnable parameter. So whenever we are coming as a learnable parameter, then means what we understood, weight and bias. So wait and bias, how it is getting updated? Automatically the value is getting adjusted. I will talk about that. How the value is getting adjusted. I'll show you with the code, right? So automatically this alpha will get updated with the learning, with the time. And X is the fix, 1 is the fix. So Y value is not a hard coded thing. Now the value will be something like this. Did you understand how we solve this problem of leaky ReLU ka solve is came with the leaky ReLU, and leaky ReLU problem got solved with the exponential linear ReLU. And you just try to understand ReLU developed in the year of 1994 and leaky ReLU developed in the year of 1996. 2-year researchers took just to update this number. And again, after that, 3 years came to develop this ELU, how to solve this problem. They come up with this thing. And this alpha is again learnable parameter. So alpha is nothing but it's a learnable parameter. Okay. So yeah. So what are the problem we solve? No need dead ReLU issue. Number 1, no need dead, no dead ReLU issue. ठीक है. Number 2, the mean of the output is close to 0. Okay, means it's 0 center. Again, it's a 0 center. So output will be 0 center. Okay. So yeah, we understood exponential ReLU function. This is again a part of ReLU only, but they have added this learnable parameter, additional learnable parameter. And the disadvantage is what? As we added the additional learnable parameter, means something new subject has been added to your syllabus. Means will take time to learn. So disadvantage is what? System computation will be slower in this case. Okay, now we are coming to the another activation, 6th activation function, which is very popular and which we are going to use very frequently, which is called softmax. Again, this softmax activation function we are going to apply always on the output layer. Okay, when your output category multi-class classification problem you are trying to solve. In that case, we should apply the softmax activation function. So whenever we are going to apply multi-class classification problem, then we are going to apply softmax activation function. So how it works? E to the power x j, we'll talk about that. A summation of k and k is equal to 1 e to the power x k, and where j is equal to 1, 2, 3. So how it is getting applied? Let's suppose you are trying to solve 10 class classification problem. Means there is a problem where output can be expected in the 10 category, between the 10 category 1, 2, 3, 4, 5, 6. So how it is getting applied? So it's again probabilistic based only. So let's suppose e to the power 1 and divided by again e to the power 1 plus e to the power 2 plus e to the power 3 dot e to the power 10 plus e to the power 2 divided by, so this thing, yeah, e to the power 2 and then not plus comma, actually it should be comma, then e to the power 1 dot e to the power 10 comma e to the power 3, and again it will come like this. It will be, we are going to consider for 10 class e to the power 10 divided by e to the power 1 dot e to the power 10. So whatever value will be maximum, that is our output. If the value is this maximum, then output will be third class. The value is this maximum, then output will be this. That's what we call as a softmax function. Okay. So softmax function is basically used for multi-class classification problem, right? Not binary class classification. You can apply softmax in the binary class classification problem as well, but again, no use at all. Then in that case, only two term will be there, right? So that can be solved easily with the what we call sigmoid activation function, right? In that case, we don't need to apply this. Okay.
So multi-class classification means that should not be continuous.
That should not be continuous. Yes, correct. You are right. You're right. Okay. ठीक है. There is a many more activation function is there, but no need to remember all those things. 6 to 7 activation function is very much enough to know about these things. So what are the activation function we have discussed? We have discussed about first activation function called sigmoid. Then we have discussed about tanh activation function, ReLU, and ReLU ka different variant, leaky ReLU, eReLU, and then softmax activation function. Yes. Okay. So we got to know about this type, and now I'm going to show you one more thing. Just hold on. We'll solve one problem with this deep learning, same problem what we solved with the classical machine learning. And I think in that case, we can develop some project as well. So let me show you some more thing what I missed it. So I think optimizer is missing still. Let me talk about optimizer. So we understood. Yeah.
Classical machine learning, PCA.
Acha, PCA is missing. Okay. No worries. I will discuss that part as well. Acha. So before discussing the PCA, activation function is clear, right? Now I'm going to talk about loss function. So this is very much. Loss function is basically what? Let me take this diagram once again, and so that I can show you. So something like this. Okay, once again I will draw. So let me talk about loss function. Okay, we have not discussed about the weight initialization techniques as well so far. So what are the things we have discussed? We have discussed about intro. Okay, then I will talk about this. So loss function. Again, this notes has been already delivered. Please follow that notes. So if we consider this diagram once again, I am making two only so that no confusion will be. This is the hidden layer, this is the output layer. Okay. So this and this. That's it. This is our x1, this is our x2, and this is our HL, right? Written there. This is W1, W2. Okay, very nice. And this is our called W3. Okay. So now just try to understand what I'm trying to say. We will get the output formula, right? We will get the output, and then what we are going to, this is going to consider y cap. Then in that case, we are going to calculate the loss, y minus y cap. Okay? This is called loss, right? This is called loss. And based on the loss, we are going to pass through the optimizer, and the back propagation is getting done. Then again, weight and bias is getting updated, so that again we are going to calculate the loss. So I am talking about what are the loss functions are there. Okay. So number one, what are the different loss functions are there? Number one is called L1 loss. So number one, L1 and L2 loss. L1 and L2 are two common loss function loss functions in machine learning. Which are mainly used to minimize the error. Okay. So L1 loss function are also known as least absolute deviation. Least absolute deviation. In short, LAD. And L2 loss function is also known as least square error. Least square error. Okay. That is the thing. Now let's talk about L1 loss function. So L1 loss function L1 loss function is generally getting used like L1 loss function is equal to summation of y true minus y predicted. Hold on 1 minute. Y predicted. So L1 loss function is equal to y true minus y predicted value. So this is L1, that's known as least absolute deviation. Why we call it as an absolute? Because here we are not going to consider any positive and negative direction. It's an absolute
magnitude.
Yeah, only we are going to consider magnitude. Now, if I'm going to consider, this is our L1 loss. You are from Andhra Pradesh, right, Trumula?
Yeah, Rajesh.
Andhra Pradesh, which place? Chikmagalur. No, sorry, it's in Bangalore.
No, Anantapur.
It's near to Visakhapatnam, or it's far?
No, that is coastal Andhra.
Achha.
Mine is Rayalaseema.
So right now you are in Bangalore.
Yeah.
So now we understood L1, why it is called as the least absolute, that we understood. Now we are going to consider another loss function, which is called L. L2 loss function. What is called least square error as well, right? So L2 loss function we are going to consider as L2 loss function equal to summation of y2 minus y predicted, you get ka whole square. I is equal to 1 to n. And now I think you have a good idea why it is called as the least square error, because this of this square.
Yeah.
Okay. So this is our L2. And the disadvantage of L2 is that when there is outlier, we can't understand. And the disadvantage is basically just try to understand what is the advantage. Again, both the function having some advantage and disadvantage. We'll talk about this function in later session. But as of now, we'll consider another type of loss function. This is one function, one loss function, which is called L1, L2 loss function, right? Another loss function is called Hoover loss function. Hoover loss function. Hoover loss function. So let's talk about what is Hoover loss function. So Hoover loss function Hoover loss function loss is often used in regression problem. Regression problem. Compared with, let's suppose I'm going to compare with L2 loss, L2 loss, Hoover loss is less sensitive to outlier. And what do you mean by the outlier? I think you know, like in my colony, remember the story. Shahrukh Khan came, the average income got increased, every people has the 1 lakh. But actually, is it? No, the Shahrukh Khan is the outlier. So sensitive, less sensitive to outlier. Okay. So because of residual is too large, it is it is it is precise function, right? So what is the how we are going to calculate the Hoover loss? Hoover loss function. Hoover loss we are going to denote like this: y comma f of x. So Hoover loss we are going to calculate like this. So 1/2 y minus f of x ka whole square. So when the value, and this is again So Hubbard delta is what? Is a set parameter. So this is again this delta I'm talking about, and the second term is, let me talk about this. This is delta y minus f of x. So two functions are there. So when to apply what? Minus 1 by e lambda Hubbard square. So this we have to apply for y minus f of x. Okay. Less than when the Hubbard, this value. Hubbard, again, it's a parameter, learnable parameter. You don't need to remember this one. Hubbard value is less. And when otherwise, the otherwise this one. So just try to understand among them this I'm talking about this delta is the set parameter. So y represent the real value and f of x is represent the predicted value. So in this case, y is the actual value and f of x is the predicted one. This one is this one. And this is delta is what? Learnable parameter. So when your y minus y predicted is less than equal to this delta value, which is learnable parameter, then this function will get applied. Otherwise, this function will get applied. So this is called Hubbard loss. And again, Hubbard loss we should not apply when we should not apply Hubbard loss when in your data there is a too many outliers are there. If your data too many outliers are there, we should not apply Hubbard loss because Hubbard loss is less sensitive towards the outlier. So in that case, you can't calculate the good amount of losses, right? So you just remember these functions. No one is going to ask the mathematical derivations again. Whatever is going to ask, what are the different type of loss function we can use? That's a need. And just basic insight. Okay, when to apply L1 loss, when not to apply L2 loss. What is the difference between L1 loss, L2 loss? What is the difference between Hoover loss and L2 loss? These things they are going to ask. That's all. Apart from this function has been developed by the researchers by their own convenience, whatever things they have found. So each and every function you should not remember at all. Okay. So again, there is a one more function. And now if you ask, okay, when we have to apply Hoover laws, then there is a no straightforward answer. This is called research. I told already, like if in your data there is a too many outliers, don't use Hoover laws. Okay. Now there is another loss function is called pseudo Hoover loss. Pseudo Hoover loss. Pseudo Hoover loss. So again, now you must ask, what is the difference of Hoover and pseudo Hoover loss? There is no difference. This has been developed by the another scientist. This has been developed by the another scientist. So they said, okay, this function also we can use. This function also we can use. That's what they made it. It's equal to delta chi square into 1 plus a by delta square minus 1. This is called pseudo Hoover loss. Now, when to use? No, it's no straightforward answer. You can apply anywhere. Okay. There is another loss function which is very popular again, hinge loss. Different type of function to calculate the losses. Hinge loss. According to the Wikipedia, people are going to use many times this hinge loss. But yeah. So hinge loss is often used for the binary class classification. So hinge loss is often used for binary classification problem. Problems such as ground truth. Truth is equal to 1 or is equal to -1. The predicted value, the y cap is equal to wx plus. So overall hinge loss we are going to apply when we have to apply hinge loss when our output is something binary class classification. When we are solving the binary class classification problem, then we are going to apply the hinge loss. And there is another loss function, fifth loss function, which is called cross entropy loss. So it's ulta. When your multi-class classification problem, then you should apply cross entropy loss. So cross entropy loss we are going to apply when we are going to solve multi-class classification. When solving the multi-class classification problem, then we are going to apply cross entropy. Again, for this, there is some libraries out there which is getting done, which will do your job, but yeah. So this is cross entropy loss function. Okay, so this is called cross entropy loss, and coming to the another loss function, which is called sigmoid cross entropy loss, sixth number. 1 minute. Leana. Hmm. So next is coming as sigmoid cross entropy loss. Again, as his name is suggesting, when you have a binary class classic, it's just extended form of this cross entropy. So just they applied when you have a binary class classification problem, then you can go with the sigmoid cross entropy function. Okay, cross entropy loss. And similarly, if sigmoid is there, then why not softmax? So if you have a multi-class classification function, then you can apply the softmax cross entropy loss. These are the different kind of loss function. Okay, yeah, these are the 6 to 7 loss from type of loss functions are there. We will see practical implementation, but as of now, this is the thing. Okay. Any questions so far? No question.
No.
No. Let's. Okay. There is a one theoretical concept is pending, which is called optimizers, and second is weight initialization techniques. Two things is pending. Then we can start our what we called practically implementation thing. Okay. So I'm thinking, can we start optimizer because it's a bigger topic and it deserves a separate class. It will take time. What is weight initialization techniques? It is smaller, no, weight initialization is also bigger. Okay, two more theories pending. One is optimization and second is weight initialization technique. Then we can start deep learning practical session. I think one more class needs for theoretical concept understanding. Then we are good to go, and then we can start our practical implementations of all those things. So yeah, so this is about today's session. We'll be coming joining the Friday about this, and Saturday we will start the practical things so that we can cover up all those things, right?
Okay.
Good. And I have uploaded these notebooks about this optimizer and loss function, all the sort of things in your drive. So feel free to start reading and making a note if you need.
Okay. And 8 o'clock today's class.
Yeah, I'm uploading. Means see, it's getting downloaded, but it should upload it automatically. But somehow it is not getting uploaded. No,
Okay.
no, right? But yeah, will get uploaded.
Okay.
Good. Good. Thank you.